In this small video, we're going to show the procedure to compute an element stiffness matrix and how we checked the validity of our computation with a mathematical program. So just to put in the reference, so when you compute a stiffness matrix, we want to compute for each function I and j the integral of grad x of Phi times the grad x of Pj over the element. Using a known map where x is a function of xi and eta, or is obtained by a finite element map, we transform this integral over the element matrix by an integral over the master element. Again, we compute the grad x of Phi at the point x of the master element coordinate, and then we transform the derivative, the unit area, by the Jacobian times the unit area of the master element. This then is transformed into a numerical integration, and so we're going to sum over the integration points the value of the internal product grad x Phi grad x Pj times the determinant Jacobian times Wp. Well, we've seen in the previous video that this part is computed using the contribute method of the math statement. So the element stiffness computation, which we're going to document, is basically going to set up the values of the material data structure, compute the contributes of the math statement, and sum the contribution over all integration points. Okay. So in order to check all this, we set up the data structure within our C++ element C++ code. So in order to check the stiffness matrices, we imported a mesh that we generate with gmesh. We created an interpolation space in which we inserted the math statements, the math statement for the volumetric elements, which we call the math statement as a Poisson, which is going to compute grad x, grad x, and the math statement associated with boundary conditions, which is basically an L2 projection. So here we go through the steps of setting those math statements, associate the math statements with the computational mesh, creating the approximation space, resequencing, and here is our verification. So we loop over the elements in our computational mesh. We define the data structure of our stiffness matrix on the right hand side. Then we do some printing of the nodal coordinates of the geometry of the element, and we compute the stiffness matrix and print it out. Okay, so when we look at the mesh we are working with, we have this here in the paraview. So we're going to check this on this mesh. Let me see if I can increase the line width. Data axis. No, I don't see how I can do that. Okay, so this is the mesh. If we look at the we can apply a shrink to that eventually so that we can see better the individual elements. Okay, so those are the elements. Now, for each element in the grid, so I'm computing the stiffness matrix and printing it on the screen. In particular, I'm going to check the values of the stiffness matrix for the last element, which I know is here, the element 121. And I'm going to identify the coordinates of this element and compute its stiffness matrix. So, getting back to the C++ code, I'm going to run my code. The code prints for each element the nodal coordinates and the computed stiffness matrix. For the last, the element index 121, I have these coordinates and the stiffness matrix. Now, what we're going to want to look at is we will validate the computation of those entries of the stiffness matrix. Okay, so let's have a look on how this is computed. Start the program again. Do a step into. Okay, so this is the computation of the stiffness matrix done at the root class, the comp element class. So first you identify the mat statement. If there is no mat statement, it's a bug. I mean, it's a problem. We can't compute anything in this case. We identify the number of shape functions. We see the number of state variables, which in our case is always going to be 1. And then we resize the stiffness matrix on the right hand side. We initialize them to 0. We take the we create an object of integration point datum, initialize it, create an integration rule, verify it's the number of integration points. So here we go. So the number of integration points is 4 in this case. Then we're going to loop over the integration point. We identify the coordinates of the integration point and the weight of the integration point. Then we compute the data at the integration point. So let's have a look at that. That's an interesting method. So compute required data. We're going to populate or to fill in the values in this data structure. So first we set the C values of this data structure equal to the coordinates of the integration point. Using the associated geometric element, we compute the value of xyz of this integration, the x location associated with the integration point. So this, if you look at that, this has been subject of one of the first exercises. So here we have computation of the integration point. We first identify the coordinates of our element, and then we compute the x value, and this computation of the coordinates has been implemented by you guys and has been validated with unit tests. Okay, so you accumulate the coordinate of the corner coordinate times the value of the shape functions. Okay, so then we compute the gradients of our map. This also been done by you. Using the gradient, we're going to compute the Jacobian and the inverse Jacobian using the SVD decomposition. Then we compute the shape functions. This also has been done by you guys. So we have the shape functions. Basically identify the order of the approximation, which is 1 in all cases in this mesh. And then we call the shape function. Okay, so this is also been implemented by you. Okay. Then having the derivatives in the direction of xi and eta of the shape function, we transform the derivatives in xi and eta using the inverse Jacobian into derivatives with respect to the axis. Okay, so this is actually quite simple method. It's computing Jacobian, the inverse Jacobian transpose times d phi dxc gives us d phi dx. Okay, so now we populated this data structure of the endpoint data. We multiply the weight of the integration point with the absolute value of the determinant of the Jacobian, and then call the contribute method, which we have documented in the previous video and also we validated. And then we do this for each integration point. We accumulate the values in the stiffness matrix on the right hand side, and the stiffness matrix has been computed. Okay, so how can we validate this value? So we've written a small finite element code. So we've written a matrix for checking a stiffness matrix. We define the values of the shape functions, define the gradient of the shape functions with respect to xi and eta. Okay. Then we copied from the C++ code the coordinates and the stiffness matrix. So this has been computed straight from those values here. Okay. Note that using this format of the eigen package, there's one little comma too much, which you need to delete in order to run the Mathematica code. And then we compute the stiffness matrix. So this is, I think, the most compact way of computing stiffness matrix for a general element. So we compute the gradient of x as the sum of the tensor products of the coordinates times d phi d, the derivative of the shape functions in xi and eta. Then the contribution for a certain value of xi and eta. First, we compute the gradient of x for this location. We perform a QR decomposition of the value of the gradient at that point. Then d phi with respect to the axis is the transpose of the inverse Jacobian times. It has to be in this case due to the way Mathematica defines the d phi, the transpose of d phi. And then the contribution to the stiffness matrix is the transpose d phi d axis times d phi d axis times the determinant of the Jacobian. In this case, it really should be the absolute value of the determinant of the Jacobian, but as my element is nicely behaved, the determinant of Jacobian has always been positive. So the value, the stiffness matrix computed, is without performing Gauss integration. You ask Mathematica straight to do the integration of the contribute in xi and eta, where xi goes from -1 to 1 and eta goes from -1 to 1. This is the stiffness matrix computed by Mathematica. We print the stiffness matrix computed by our finite element code, compute the stiffness matrix from Mathematica, and then we take the difference of Mathematica matrix, our matrix minus Mathematica matrix, divided by the correct value times 100. So that gives us the error of each term as a percentage. Okay, so what do we obtain? So let me execute the whole thing. Some problems with numerical integration. Wow, it's all zero. That's not good. Is this the absolute of the determinant of Jacobi? This code was working.
Eu falei, o que é isso aqui? Uma coisa estranha?
So let's compute it again. Okay, that's better. So this absolute value was wrong. So this is the value computed by the element code, the C++ code. This is the value computed with Mathematica. You see they're not exactly equal. There is some error due to numerical integration. So in the fourth digit, the values are different. And here we have the values of the error percentage-wise. So you see our numerical integration is quite precise. It is precise within 0.2% of the value of the stiffness matrix. Okay, so this is what I wanted to show. We have computed a stiffness matrix using our C++ code. We imported the coordinates of the C++ code in this Mathematica code here. Okay. And with these coordinates, we computed the exact integral or almost exact integral using Mathematica and compared the values, and we've shown that our C++ code gives almost the same result. The fact that they are not the same should not worry us. The error due to numerical integration will influence the final result, but less the error will be such that it does not affect the convergence rate of our computations. So it's good to know that our numerical integration is an approximate integration, but the fact that it has 0.2% of error is not something that we should be worried about too much. Okay, that's it.